I see Sam is not here.
Yeah,
it's a very solid presentation. And this presentation is about a paper named Information Theory Approach for Privacy Metrics, which is a paper I read a few months ago. And here's the outline of this presentation. The motivation of this paper is to provide a common framework in the information theoretic perspective, which is able to express different privacy conditions. Here is the outline. We will start from a quick review about the problem background, and then we will recap some well-known privacy-preserving data dissemination method I talked a few weeks ago. Finally, I will present information theoretic interpretation of those aforementioned algorithms. Organizations such as the hospital or government agents usually connect to the microdata such as the medical report or resident record, and regularly release them for research purposes. For example, a prediction model can be built based on the medical report to provide decision support for doctors, and the U.S. Census data can be used to help officers make some decision for planning purpose. On the right hand side, it is the voters registration list, and on the left side is the microdata about the patient. As we mentioned before, the release of the medical or census data has great benefit. However, such data contains many sensitive personal information, and the improper disclosure put the privacy of individuals at risk. For example, findings in an earlier study shows that nearly 87% of U.S. population can be unique identified based on just the zip code, gender, and date of birth. Therefore, there's a conflict exists between the research benefit and the sacrifice of the individual privacy. There are some solutions for this problem. One workaround is privacy-preserving statistical analysis by using differential privacy framework, where the data owner must be aware of the data mining activities in advance. Then they can customize the anonymization to preserve some statistical properties. However, for the general purpose privacy-preserving data dissemination, for example, we want to create testing data for applications or outsourcing the development of new data mining algorithms. We need to develop some effective privacy-preserving data dissemination method. In the next, we will provide a brief review of some popular existing algorithms in this area. Here is a medical database. A medical database usually contains a key attribute such as the social security number, and which can be used to directly identify an individual, and the quasi-identifier such as the zip code or the age or gender, which can be used to re-identify an individual with some additional side information, such as the voters registration list, and the sensitive attribute whose disclosure can put the individual privacy at risk. To protect the privacy, the key attribute will be removed before the publishment, and then the record are partitioned into equivalence class, where the quasi-identifier in the same equivalence class are replaced by a single generalized value. For example, we can see on the left-hand side we have an original disease table, and on the right-hand side we have 3 equivalence class. And in terms of K anonymity, we can see there are 3 identical records in each equivalence class. So in this case, K is equal to 3. And this table is also satisfies 3 diversity, since there are 3 distinct diseases in each equivalence class. Here we have 3 different diseases in each equivalence class. And this table also satisfies 0.2 closeness, since the difference between the sensitive attribute in each equivalence class and that in the whole table is less than 0.2. Here the 0.2 is calculated in terms of the KL divergence. And this presentation tried to get connection between information theory and for mentioned 3 different anonymization methods. And let's first give a recap about the information theory. As X and Y are 2 random variables. For example, X can be the causative identifier in a data set, and Y can be the sensitive attribute in the same data set. And we can define the mutual information like this: IXY equal to the to this formula. Here, Px and Pi are the probability density function. And we can see the mutual information summarize the average amount of knowledge we gain about Y by observing X, or vice versa. The mutual information is non-negative, which means any observation does not decrease the knowledge we already have about the system. And since the mutual information is the average quantity, for some applications it is important to know which is the contribution of a single symbol, such as a single value X or Y. In the rest of today's presentation, we will focus on 2 one symbol specific information. We name the I1 and I2. Here, I1 can be expressed as this, and I2 can be expressed as this. And we call I1 as a surprise and I2 as a specific information. I will give more detail about both one symbol information. First, this definition can be for the I1 surprise. This definition can be indirectly inferred from the definition of mutual information. We can see according to the Bayesian rule, we can express the joint distribution in this formula, and then we can get the I1 in this formula. If we average I1 with respect to the variable X, then we can get the mutual information. And this quantity measures the KL distance between the marginal distribution Py and the conditional probability distribution Py given X. And here are some properties of I1. First, I1 is non-negative, since it's the KL divergence between the Py given X and Py, so it's non-negative. And the average of I1 gives the mutual information, as we just saw in the previous slides. And we can see for I1 it's very large when the Py given X dominates in the region where Py is very small. This is why we call I1 is surprise in this event. And any questions? Let's continue. So for the I2, we call the specific information. We can express the mutual information IXY in terms in the forms of reduction of entropy. Then we can extract the single symbol contribution from the sum and obtain the specific information I2. Here I2 is identified with the reduction of entropy between marginal distribution Py and the conditional probability Py given X. It expresses the difference of uncertainty between prior knowledge of y, Hy, and the knowledge of a given symbol y, given symbol x, h, y given x. Here are some properties of I2. We can see I2 is no longer non-negative, so I2 can be negative, and the average of I2 also gives the mutual information. Now let's get a connection between the information theory and the privacy risk. Suppose IWX and IWX had the mutual information between sensitive attribute and coded identifier before and after a normalization process. Usually, we need the mutual information between W and X hat is smaller or equal than is equal or smaller than the mutual information between W and X. Hence, the privacy is protected. For the K anonymity, for a single equivalence class X tutor, which corresponding to nx tutor, a number of records in the original table X, the probability of identify a record given X tutor is simply P X given X tutor equal to 1 over nx. In K anonymity, we need in each equivalence class there at least a K number of identical records. So to satisfy the K anonymity, we need nx tutor is equal or larger than K. Then we get the formula, the following equation. And if in terms of this equation is very intuitive, we can just take an algorithm of both sides of this inequality, and on the left hand side we sum over the n number of probabilities, then we can get the entropy here. And in terms of the one symbol specific information I2, we can get I2 equal to the hx minus hx given x tutor must be equal or smaller than of 2 of n over k. Here n is number of records in the whole database, and those I2 measure the identity disclosure risk for a single record. By average I2 over x, we can get the mutual information must equal or less than of 2 of n over k. Here is a necessary condition, but not a sufficient condition.
Did you say again how to find the first equation?
You mean how?
Is this then?
Yeah, it's come from here. in K anonymity, we require in each class there at least a K number of fractals, right? So X increments are equal or larger than K. Do you understand this?
Yeah.
Okay. So we take a algorithm on both sides.
Oh.
Right? And we can add a minus sign. Right. So we sum over for all inputs. Right. So what's this? Oh, there's one. This is the entropy of P. So to satisfy a K anonymity table, we must be satisfy this equation. So
You can do that for I.
yeah,
Yeah,
and we know I has this formula I equal to H times so we substitute this equation into here because here is a constant for a given table. So we can get this relation. So for K anonymity table, I2 must equal or smaller than this this quantity. So this is the connection between K anonymity table and the information theory in terms of I2.
How about HX?
Oh, Hx is equal to
Okay, yeah.
is constant.
Yes.
So here's the connection between information theory and the t-closeness. In t-closeness, we need to satisfy by this equation, which means the difference between the sensitive attribute in each equivalence class and the that in the whole table is smaller than a threshold t. And this is equivalent to the one symbol specific information I1 according to our definition. So we get I1 equal to this formula is bounded by a threshold t, and also by averaging the I1 we got the mutual information. This mutual information is also a necessary condition, but not a sufficient condition. And we can see the difference between the knowledge of entire distribution PW and the posterior wave PW given X after having observed X and corresponding sensitive attribute should be bounded by T. So this is a connection between the t-closeness and the information theory framework in terms of I2. And we can also get the connection between L diversity and the information theory. And in the L diversity, we need the entropy of we need the entropy of each sensitive attribute in equivalence class is larger or equal than a threshold L, and this condition can be expressed in terms of one symbol specific information I2. Here I2 is a measure of attribute disclosure risk of a quasi identifier group as a reduction of the uncertainty between the prior distribution and the conditional distribution. And so that's all. Yeah, I read this paper a few months ago and prepared this presentation 1 hour ago. So any questions?
Did you apply this method on that the problem that you just showed about the illness? You know, yeah.
Oh yeah.
Did you apply that on this one?
Yeah, sure. We just want to get connection between information theory and the
How is that? The result is better than the other result?
There's no improvement. I mean, they just use information theory to interpret the three well-known.
Just show that this one is possible. You can just use the information theory for that.
Yes. Because no one did that, so
Yeah.
they got the publication.